But the second reason, maybe more important, is I felt there's a clear gap between research and industry or application, or a gap between academia and industry. It's not like people don't talk to each other, but people tend to look at the world from their perspective. And then I thought maybe I can do something to use my knowledge to make something tangible and offer it to the market. And that motivates me at that time, and it's still motivating me now. The company TEGnology was founded in 2011 based on the patents that I was involved. At that time, I was offered an opportunity to work in the company as the engineer. I thought that I think that was the good opportunity to use my knowledge and also to explore, at that time, a strange word for me, which is the industry. In the early years, yeah, it's a long time since 2011, we were focusing on regenerating heat from the exhaust pipes of diesel engines, the big engines. At that time, we have partnership with a very big vehicle manufacturer. And then in the year of 2015-16, we actually built a prototype that we can be mounted on the diesel engine and reharvest energy and generate about a few hundred watts electricity. It was not that bad. I actually still keep that first original prototype at the back behind me. But then, as you might imagine what happened, at that time when we present this to the manufacturer, they told us that the market is shaky because the vehicles will be electrified, even though the heavy vehicles will stay with the combustion engines. But it's more difficult for them to commit further R&Ds into traditional combustion engine. So for us, it was really a disaster that so our biggest market disappeared. Then we discussed what shall we do as a small company with no customers, and we have some investors, but as they know that the market disappears, they quit it as well. And then we say, okay, maybe it didn't work. We should just close the company and find new jobs. But I still believe in the solution in general. Thermoelectrics. I still think it makes sense, and it's interesting that the vehicle market disappear only because that market disappears, but doesn't mean that we cannot use it for in other applications. Therefore, I decided to move on with the company. So, as mentioned at the time, I was just an employee, and since we have no income, no investors, the company actually cannot afford to give salary to me. And then, in Denmark, it's illegal to work without salary. Then the only way that I can work in the company is I become the owner of the company. Then nobody cares, right? Because I'm running on my own risk. So for that reason, I became the owner, at that time, the co-owner of the company. Then you can say to some extent, I was not chosen to my current career. I was just given, right? And actually, if I knew it was so hard after that, I would probably not take the choice. But I guess sometimes you just don't think too much, and then you take the risks and see what happened. And then since then, fast forward to 2019, we have pivot. We have packed the solution into a new solution that instead of generating electricity from the exhaust pipes of vehicles, we harvest small energy, small temperature difference, and generate small energy to power sensors. This is not not the new concept either, but we just make it happen with offering products. So these harvester, or we call it generators, can, when you attach it on the surfaces, it give you some small power, sub-watt, milliwatts power, so you can drive your sensors. And then we also find some unique applications. Some people call it the niche applications. That it's actually quite unique because you have no alternatives. It's underground, it's difficult places with harsh working environment that batteries are not welcomed. So this become a real product and now have been purchased again and again by some world-leading manufacturers to monitoring their production. So the reason I share you this, my personal story with the company, is it's not easy to commercialize thermoelectric solutions. Well, I guess it's not easy for commercializing any new technologies because we always have this chicken and egg problem or paradox. Without a customer, you cannot convince the investor or anyone that this is a promising technology. And without investors' investments, you cannot find customers or further develop your solution. And then, of course, you can find you can apply for grants and grant fundings. But again, that was only meant to be R&D, right? You cannot use that funding to hire a salesperson. So it's always difficult. My point is, when I talk to people, sometimes I got the feedback that people saying, yeah, I know thermoelectrics, I heard about it, I used about it. It only suitable in niche markets. But now I thought my reply to these comments would be like, think about which new technology that doesn't start from niche markets or niche applications. Actually, all of them. Because when you have something new to offer to the market, the people haven't thought about or people didn't see it, the first reaction is, why is it relevant to me? I'm doing, I'm living fine. Why should I try the new stuff? And think about the solar panels, right? Now it's probably one of the most important renewable energy source. But if you remember, only maybe 20 years ago, the only application of solar panel is this tiny windows on the pocket calculator. I remember that. And who could imagine that at that time that now everyone want to install a solar panel on their roof? So I'm not afraid of being in the niche market. As long as we can find the real value, we find a unique application that our solution does bring value to the customer, then it's a good start. And from there, we can roll up the implementation of new technology. And another difficulty is another reason why it's so difficult to commercialize thermoelectrics is there are many, many myths. I call it myths or misunderstandings. And today I want to bring some of you on the table. Well, I will just by the way, yeah, this is the team. Maybe I will come back to this. Let me go direct to the myths. Thermoelectrics. Many people saying the impression of thermoelectrics when they think about it is the efficiency is too low, so it's useless. I'm sure you have heard about this comment. But the reason I call it myths is it's not true. At least it's not completely true. Because efficiency is always relative. And think about the combustion engine. I like combustion engines, not because it was our first market, even though it didn't work out. Is when we tank fuel, gasoline or diesel or benzene into our tank, only 25 or 30% goes into the momentum of the vehicles. All the rest is lost in the air. But nobody talks about that, right? From the energy point of view, all the fossil fuels should never be burnt, because burning fossil fuel is actually a very low efficient manner of using the energy that was stored in the chemical bonds. But we don't care, because the profit or the benefits of burning fossil fuel has bigger value to us. It brings us to a difficult place, another place where we couldn't without combustion engines. Another example is the photonic synthesis mechanism, where the plant transfer the solar energy into proteins. Again, from the energy point of view, it's only a few percent, 1 to 2%, that the plants can convert solar energy or energy from the sun to proteins. But it is those few percent that support every living species on the planet. So efficiency is always relative. It depends on what the effect, or actually it's the cost effectiveness, which is more important than efficiency itself. Thermoelectric generators does have a low efficiency compared to combustion engines or Rankine cycles. But it doesn't mean that we cannot use it. It doesn't mean that we cannot use it today. We should think about the applications where efficiency doesn't matter that much. And then by doing this, we can maximize the impact of thermoelectrics. Myth number 2. Thermoelectric generator will become a major power supply solution in the future. My opinion is it will never happen. Think about solar panel. I take solar panel as an example again. That converts visible light into electricity, as we all know. But the areas that the solar panel absorbs light, the energy that is projected to these areas is actually much, much more than the visible light. Visible light is only a tiny bit of the spectrum that was carried in the sunlight. And we only use a tiny bit of it. It's the visible light. Energy-wise, heat, the energy that is carried by heat, infrared visible lights, is much more than the light itself. So if we analyze the energy, we should actually use thermoelectrics instead of solar panels to generate electricity, despite that TEG, the efficiency of TEG is lower than solar panels. But not to forget, solar panel, when they started commercialization, the efficiency is not much higher than TEG today, right? However, the solar panels have already taken the place that should have been used to implement thermoelectric generators. But in that competition, thermoelectrics have already lost. There's no way that in the future that we can compete with solar panels, because solar panel has already reached the mass production phase. So when we think about thermoelectrics, we should not talk as if it will be comparable with solar panels, windmills, or some other technologies that will be a major player in the energy spectrum. But it doesn't mean that we shouldn't develop thermoelectric energy. But because when we say no to something, we have the new ideas of where we should look at. We should not compete with the existing technology, because thermoelectric cannot compete with them. Myth number 3. The materials with higher ZT is all we need to commercialize thermoelectric energy harvesting. I'm not saying this is wrong. It's absolutely critical. It's absolutely important and needed to further searching for new materials and doing material engineering to modify the materials so we have a higher ZT. We should do by all means. But we should also remember that this is not the only critical things in commercializing thermoelectrics. In the early years of technology, when I was the engineer, I got an opportunity for, it was 3 years that I was alone in the labs, that I spent days after days and even the evenings. I even slept in the floor of the labs just for going through the manufacturing procedures from when you have a powder, to the raw material powder, to the final modules. I've actually gone through all the single steps by myself, manually. So I know how much details or how many details are hidden somewhere that we don't talk about when we, try to improve the ZT. And I also learned that the very single or tiny carelessness will ruin a high ZT material. So, in other words, from a material with high ZT, there's a long way until we have an efficient generator. So we should, on one hand, keep searching for new materials. Now we have AI, we have all the smart things, so we can screen the materials much faster than before. But on the other hand, we should remember that doesn't guarantee that we will have a working module. And more importantly, that it will guarantee that we have a profit product. Because to the end, we are going to put our solution, a TEG, on the market. And the customer is going to compare it with all the possible alternatives. Even though we talk about, I start talking about we should find the unique applications where thermoelectric generator is unique. But still, people always try to find alternative or existing alternatives. For example, if we say we power the sensor, the small sensor nodes in difficult places, the IoT sensors, but people can always use batteries, even though it's not a sustainable way, right? Even though it sometimes can be difficult to change it, but the cost itself for the batteries is very low. And if we say the power, the electricity is the product from the TEG, then we cannot stop people from comparing the electricity price that they get from the grid to the electricity that we generate. And as you can imagine, that there's no way that the kilowatt hour electricity or the kilowatt hour price of the electricity generated by TEG can compare with the price that they get from the grid. That's why it's a big myth that high ZT material is all we need. It's much more than that. And then comes to the following question, the perspectives. Where the future of thermoelectrics is. I put a question mark there. I'm not that pessimistic. Thermoelectric is all I know what to do. I first get in contact with thermoelectrics in my master degrees. And then in the last almost 20 years, this is the only thing that I'm working with. And it's probably the thing that I'm going to work in the coming 20, 30, 40 years of my whole career. So I also want to know where is the future of this technology? What's the future of this small company called TEGnology? And what's the future of me, myself? But unfortunately, I don't have the answer. But I know that we need to work together. We, as a startup, as the owner of the startup, I'm doing so-called pitch. I need to convince the investors to put some money into the small company. I need to convince the customer to try our product. And all in this pitch, that I need to tell them where the sort of the future is. What I want to say, I actually get lost of what I want to say. Just give me a second. Oh yes, when we talk about competitors, the customer always asks, what your competitors are doing. The investor was asked the same. But for me, it's like it's too early or too short eye-sighted to think who is the competitors in thermoelectrics when thermoelectric generator market is such a small market. It doesn't make sense to say that I compete with you, you compete with me. We should join the force to solve all the challenges and all the problems in bringing thermoelectrics to bigger markets. And there we actually need all kinds of helps and all kinds of collaborations. Besides the R&D itself is of course based on collaborations, but also marketing, right? So I was trained as an engineer. I have no way how to tell a good story. People say a good salespeople can sell sand to Sahara. Sometimes I have difficulties in trusting what I'm saying by myself. Then how can I convince our customers to say, stop using batteries, using thermoelectrics to power your device? But we have to learn the skills. And the suppliers. Now we have products, we're commercial products. We can do some assembly and small tweaks in the labs. But as the order increase, can we produce hundreds of thousands of pieces in the constant quality? And where do we get this enough material? Where do we get them produced? Where do we get the wafer sliced, get the legs assembled? And all this detail, don't remember, I've said a single tiny mistake will ruin the entire module, will ruin the entire high ZT material. And all that needs a supply chain to support. And this supply chain is missing, at least missing in Europe. We're still highly relying on the material supply from China, from Russia, and also most of the assembly is manually done in these two countries. And apparently, that's not the future of thermoelectrics. With that, I will come back to the team that I'm most proud of, and also the product or the core innovation that we contribute to the market. And that is a flexible TEG. And now, without using the ceramic substrates, it's polymer, so we can actually bend it in different areas, different angles. So it's much easier to apply it on any other non-flat surfaces. I have a demo here, so you know what we're talking about. This is, I think I can claim the world's biggest single TEG module, a single cell, that is bendable. You can bend it in both ways. Okay, I will stop here. I will be glad to hear any questions or comments. Thank you very much.
So, thank you. Can you hear me? Yes, probably yes. Thank you, Hao, for your presentation. We have some time for questions, as I wrote in the chat. You can I think starting from now, because I changed the mode, you should be able to switch on your microphone if you want and ask questions directly to him. If there's anyone who has questions or comments on what Hao said, because it was more or less, let's say, some philosophy around the issue of the thermoelectric devices. So maybe you have different views. Can we have some comments here? Does anyone want to say anything? Everyone is shy. Oh, yeah, there's someone coming. Yes.
It's me, João from LNEG. Okay, I just had a little question here about the prospects. You told us that there is a problem in the supply chain today. Do you think that we
I'm sorry, Jay.
Yeah.
It's a bit difficult to hear what you're saying.
Sorry, you hear me?
Yes,
now
yes.
I hear much better. Please continue.
Okay. So I was talking about the material supply chain that nowadays you have it mainly from China. Do you think with the START project we can enhance this supply from Europe?
I definitely think this is a good attempt to strengthen the supply chain of Thermoelectrics. But I would not say that from the single project that we can change the scenario of the entire Europe. But it's a very good starting point. We need to take the whole picture of the entire supply chain. Does it make sense?
Okay. Cheers.
So from the supply of the raw material to handling, purification, synthesis, and all that following process needs to be considered when we talk about supply chain.
Okay. It's a start.
Yes.
I think the next was this PL that is on screen. I don't know if it's Paulo Lutz, maybe. Is it you? Can you switch on your microphone? Hello? Don't hear you very well. So maybe it's better if you post in the chat. Yeah. Thank you. There was a question from. Sorry, very noisy. There was a question from Elia Villa. What are the thermoelectric materials used for the flexible thermoelectric?
Good question. We can put any materials we want into, or our customer wants into the flex TEG, because the design itself is not specified to any specific materials. We do have bismuth telluride as the business as usual, but we also have magnesium silicide as newly developed and tetrahedrite that is possible to put. We're actually doing that to put that material into FlexTex.
I hope that
so the
helps.
design itself it's very versatile.
Thank you. And there's another, I think, SM on screen. If you want to speak, yes, you were first.
Hello, everybody. Thank you so much. Thank you, Hao, and nice to meet you.
It. Good to see you.
Good to see you. Very inspiring, and I'm like always, I'm learning a lot from you, and very encouraging speech. My name is Said Mahmoud Mortazavi. I'm from a company called Parsnor Thermoelectric. We are based in Sweden. Somehow we are doing similar thing to how we are trying to commercialize flexible thermoelectric device with the same concept and using for IoT applications. I'm here mostly to, hear about your projects and learn, many things like always from you. But how I'm curious in this specific project, you are using tellurium-free material for making flexible thermoelectric devices. I just didn't get that.
Yes, in START project, it's the mineral tails, the mine tails, is the tetrahedrite that we use.
Okay.
But then, of course, also with other material, because tetrahedrite are mostly N-type, P-type.
P-type.
Okay.
P-type. We also need N-type material.
Perfect. It was like a huge device, by the way.
It can also be small. I didn't
Okay.
show it. And we also have a small bendable devices.
Nice. Yeah.
So,
Yeah, it is nice. Thank you so much. And good luck. Thank you for sharing.
thank you. You too. You too.
Good to see you again.
You too.
Thanks. Maybe we can take still the question that is on screen, and then maybe you can answer in the chat to the other question that was there. Who is there? RC Radion, maybe? Yeah. Can you speak? No, he's disappearing.
Oh no, he wrote
what's the ZT of this material? Okay, yeah.
Around 1.
Yeah,
it's around 1.
True.
And I think there's a question: the thermoelectric solar thermoelectric, so combined solar and TEG. I don't think it has been commercialized. we are one of them who is still working on it. What are the main challenges hiding their adaptation? Cost effectiveness. PVs are so cheap nowadays, but actually it's an interesting question, because the competition of solar panels are so severe that some of the manufacturers starts to think about how can they make the current design or solutions more efficient, maybe by adding thermoelectrics. So the biggest challenge is apparently the scale. How can we scale thermoelectrics in the comparable scale as the solar panels?
Square meters.
Square meter. We're talking about hundreds of or thousands of square meters for a solar panel park. And then if we do that, so none of the existing supply or design of TEGs is suitable for that. We need to start from scratch.
Okay, sorry, I will have to stop here, but we can have some more time maybe at the end for the other questions, so that we can have also the second speaker now on stage. Thanks, Hao, for the moment, and we will have you later maybe. So I go back to the previous structure and back to the presentation mode, so that now we can have on stage the second speaker, who is Aniruddha from RGS Development, another partner of the START project. But he will present himself, I guess, and his company, and you can share your slides as well.
Yeah, sure.
Thanks, Ani. The floor is yours.
I hope you're able to see the screen. Okay, I take that as a positive. Hi, I'm Aniruddha. I'm the Technology Development Manager here at RGS Development.
Sorry, it's not a yes, because I still don't see it. Can you try again? It says screen loading, so maybe now I see your session. Now it's perfect. Thank you.
Perfect. Okay.
Thank you.
Yes. Yeah. So indeed, nice to see you all. Good afternoon. I'm Aniruddha. I lead the technology and development team here at RGS Development. So we are a small company based in the Netherlands. And in today's presentation, I'll give you a bit of a perspective of what it is to be like a thermoelectric module manufacturing company in this field. So the presentation itself is cascaded into 2 ways. So first, I start off with the product portfolio, and then I structure the presentation based on the 2 applications that we have been targeting. So here at the bottom, you can see some of the pictures of our production facilities, how we think about our products and the integration in the systems and the final applications. So here, taking the space application as a kickoff, we started off with our products where we designed this 100 by 40 base module, so 100 millimeters by 40 millimeters in size, what we called a TEG module, similar to solar modules, which can generate 10 to 20 watts of electricity. And we have started stringing them together into larger panels to generate up to hundreds of watts of electricity. We have also imagined kind of circular configurations to interface with different kind of incoming heat flux sources. So these devices we have started producing in our plants, where we patented a way of making silicon germanium based materials, where we have built up vacuum induction furnaces from scratch, where we melt the material, cast it, and do all the downstream process of polishing, dicing, as well as assembling the final devices in a brazing oven. We also upscale the production process, imagining an entire 24/7 running kind of process where we can make these kind of wafers in batches as and when needed. So talking about the upscalability, indeed, if you want to make something which can actually fly in a real application, you need to make sure that the production process can be tuned such a way that the costs are low enough. So here, these devices, where after we produce it, we do extensive testing. Here you can see some of the tests that we have done with our all silicon germanium-based modules. So we carried out these kind of endurance tests, testing it up to 10,000 hours at 600 to 700 degrees centigrade. It's able to generate around 2 kilowatts of electricity per meter square. We also did stress tests where we expose the module and especially hot side above 1,000 degrees centigrade. And we look at what happens at the bonds. And indeed, the bonds are quite stable. And that is key for applications where you might have some kind of thermal shocks. For example, you can imagine waste heat recovery. We also patented the way of bonding these kind of materials such that it's quite tunable. As most of you are thermoelectric engineers and material scientists, you might know that for a basic TEG device, the way you tune it is the fill factor and the heights of your pellets. So this kind of harmonium-based design is quite adaptable for that, depending on the application. So for now, I described to you our way of producing the material as well as maturing it into a product. And this we had actually carried out in a Horizon EU funded project in the past called Integral. And similarly now, we want to expand this product portfolio. So here you can see how we name it. So this is our brand name, the Thermoelectric. We are looking at maturing a mid-temperature module, which I will talk about, which is the main aim of the START project. And then we have the Thermoelectric T, which I showed you just in the last few slides, targeting 50 to 850 degrees centigrade in operation temperatures. And then we have another one called the Thermoelectric S, which is for space applications, where the requirements are a bit different because the mechanical requirements start playing a bigger role. So you need robust pellets. And finally, our idea is to start looking at a cascaded module so that you can actually tap into the entire temperature delta T, going all the way from 50 to 850, using the materials which are suited to the respective temperature zones. With these products, we want to target specific applications. So waste heat recovery, combined heat and power, which is for heating your homes as well as generating power as and when needed. With the Thermoelectric S, we are targeting radioisotope thermoelectric generators. That has been one of the niche applications of TEGs, which has met with a lot of success in the last few decades almost. And with the Thermoelectric C, we want to target thermal batteries. I will come to this application towards the end of the presentation. So to begin with the first application area, radioisotope power systems. I think a few of you might be quite aware of the Voyager satellite and quite a few of these rovers which have landed on Mars. Most of them are powered by thermoelectrics. So that has been one key successful applications of these materials and these devices. you can see that depending on the requirement and also depending on the type of fuel source, different thermoelectric materials have been used. So the one on Mars was based on lead telluride tags, while in the upcoming decades, there is going to be a new mission for up to, which will require up to 285 watts of electricity, especially towards Uranus. That has been the targeted mission. Here, RGS is a key partner as a material supplier for this project. And this is something we are quite proud of, because we are learning how to mature these materials and as well as use them in a key application. On this side of the ocean, ESA is developing a more compact system, which can generate up to 10 watts of electricity based on americium sources. So that's another type of fuel source. And this specific one is actually in line with what a lot of, say, space research organizations from around the world have been targeting, and that's the lunar pole, the South Pole. In just the last few years, they have found a lot of resources in the lunar South Pole, some ice which can serve as potential, habitat kind of nature for future explorers. But none of these landers were able to survive the lunar night, which is basically 14 days where you have no sun. It's permanently shadowed, so you can't even run your solar panels. You can imagine this is the perfect application zone for TEGs, where solar panels cannot survive, and you need to run your electrical devices and keep them warm throughout this period. So that's where the need comes in. That's the pull. However, qualification of a certain fuel and a system architecture is long. So once that is done, and that is what NASA does or ESA does, the need is to come up with a versatile conversion technology like our TEGs, which can fit such a qualified fuel architecture. So here we proposed on starting with the tried and tested silicon germanium materials, which can serve multiple levels of power depending on the needs of the electronics. And it can conductively or radiatively couple with such an incoming source. One of our key partners for such a project was UDRI. It's a research institute in the US, where we started with this kind of pre-qualified thermal brick, which has been designed and qualified by NASA. And the idea is to couple two of our TEG modules conductively so that we can generate up to 14 watts of electricity with an incoming heat flux of 250 watts. We're already in process of testing this. We're going to be maturing the design, and we are looking forward to increasing the TRL level, which is the technology readiness level, so that it can fly in the future. So a few key takeaways from our endeavor in this space-based applications is that the conversion technology has to fit for a pre-qualified system. So in order to fit, it has to be quite modular. So a different kind of power supply needs as well as interfacing needs. The mechanical characteristics of such a module has to be robust enough, and it has to be simple enough. And meanwhile, in these kind of projects, you have to be quite quick. So you have to iterate very quickly, going from simulation and modeling to manufacturing within a constrained time period. So we did this within 8 months, this entire kind of module fabrication. So that gives you a glimpse of what we have been doing in the space applications. Now, our idea is always that what we learn in space, we want to bring it to Earth. So terrestrial applications, that's where the large kind of application areas are there. Here, you can see at the bottom, right here, one of our applications that we are targeting, which is the combined heat and power. So the idea would be to integrate the TEGs with a boiler so that we can not only generate electricity, but also with a heat exchanger, convert that incoming heat into a heat that can be used with, for example, hot water for your bathroom taps, as well as for space heating. Here, we have also been targeting another key application, which is waste heat recovery. So we took our TEG modules, we made entire systems out of them. So you can see in the top left picture here. So entire panels of them. And then we exposed it to high temperature steel at 900 degrees centigrade, as well as in LChem, where it was basically a molten silicon, so even higher temperatures. It's a very corrosive as well as a high temperature kind of zone. So your materials have to be stable, your bonds have to be stable. It should be able to take thermal shocks because it's not a continuous casting part of the steel factory. So it can go up really high in temperature, and then suddenly it drops again. One of the key learnings we had from this application was that generating electricity was part of the picture, but the other fact is that at the back of our TEGs, we could also generate a lot of good quality process heat, so up to 8 to 20 kilowatt per meter square of hot water and steam, which can be reused in the industry. So with this combination, they get a double benefit from such TEG modules. In this plot, you can see some of the characteristics of our all silicon germanium based module. It is quite good, especially above 500 degrees centigrade. That's where these silicon germanium materials start performing. And when we notice this gap, we started looking at some more materials which can operate better between bismuth telluride, which is max 150, 200, and up to 400 degrees centigrade. So there clearly was a gap over here. And that's where what we started targeting in the START project, which is being led by Filipe, who was there at the beginning of this webinar, where we are looking at tetrahedride materials and combining it with an N-type material. And in order to develop a TEG module for these CHP boilers, so waste heat from heat generation for combined heat and power applications. Here you can see a schematic of the entire project where we are going from material processing to simulation to device and finally device integration in a follow-on after this project. So we want to make something which can actually fly and can generate something. One of the main key objectives of this call was to look at upcycling mine waste materials. So there are a lot of sulfide mines around Europe where you have just these mine tailings which are lying open and they can be reused and integrated to an actual material and actual device. So we're looking at circular feed supply of such raw materials and specifically the tetrahedrides. So we have got quite some promising results from the materials, which will be shown in the upcoming webinars. And we have also already started doing all the processing steps for such a module. So milling in large batches, sintering the discs, and then characterizing them so that we can simulate the optimum unicouple dimensions so that we can get the right temperature deltas across the module. So we have started producing our first modules. You can see it on the right side over here. We simulated it, and then we made all the tooling so we can get an application-dependent TEG module. So with the optimum fill factors as well as heights. Now you can see that within our company, we have these kind of two modules. One, which can operate at high temperatures, and potentially within the START project, a Thermoelectric M, which can operate at mid temperatures. One of the ideas was to start cascading these two. And here, I'll just give you a brief glimpse of what we are thinking about to use such a Thermoelectric cascade for a thermal battery. So I think you might have heard of this concept of the thermal battery because it has been proposed as a solution for storage of renewable energy, which you generate during the day so that you can use it at night, for example, in the evenings when there is no sun around, right? That's when the use actually starts peaking. So in the BlazeTech project, which is another EU-funded project led by CNR, we are looking at using TEGs and other conversion technologies to convert the heat from thermal batteries, which is used for storing surplus renewable energy from solar panels, concentrated solar power at really high temperatures. So even the energy density is really high. So that's a project which has been kicked off in July 2024. So where also the results will be upcoming. Indeed, we are quite interested in working in these kind of EU projects, which allows you to do core R&D. But being a company, we always get into these projects with a view of integrating them into real products that we can make, products that we can test at scale. So here are a few key takeaways. From the space-based applications, we realized we need a conversion technology which fits a pre-qualified system architecture. While in terrestrial, we needed a solution for the various temperature zones that can allow us to get to high enough efficiencies, especially for combined heat and power applications. With that, I want to open the stage for any questions, and please feel free to contact me in the future. I would love to hear from you all.
Thank you, Ani, for your presentation. And again, we can open the stage to questions. And now you should be able to switch on your microphone and camera if you want to ask something directly to Ani, or you can post a question in the chat. And again, don't hesitate. Yeah, there is something in the chat. So what is the silicon germanium ratio of the silicon germanium used in the module? First question.
Yes, so we are able to produce all the alloys, and typically we use from 10% germanium up to 25 to 30% germanium.
Okay, and are the N-type and P-type legs P-doped and B-doped silicon germanium systems respectively?
Yes, indeed, it's from the same family, and we dope it with phosphorus and boron.
Right. Any other? Another question? Yeah, thank you for the excellent talk. What are your current production capabilities in terms of modules per day?
So right now we do it more like for solutions. So we try to look at integrating the entire TEG along with the system. So we don't supply individual modules as needed. So now we look at projects where we can the subsystem integration. That's what we are targeting.
Right. Any more questions? Julian, what is the price of the Thermo GT and the other products?
Yeah,
Right.
that's a good question. We can always get in touch later about this.
Yeah, I think so. Any more? Remind you that you can switch on your camera and microphone and ask directly if you want. Now it's possible. Everyone is shy now. But keep in touch, because we are, as Ani showed, the modules are coming from the START project. So we will soon show something more specific to the START project results, right?
Yes.
I don't know if you can say something more about that, just saying without showing.
No, indeed. So as I was showing you that you can see over here, we're already designing and producing modules based on these materials. And the materials are looking quite promising. The key is about, again, bonding and testing this long term, right?
Yeah, and as Hao mentioned, even the ZT is quite interesting.
Yes.
Even if it's not maybe so necessarily important to be at very high levels.
Yeah. Yeah.
Okay, I don't see any other questions at the moment. There might be more maybe at the end. So I would thank you again, Ani, for the moment. And let's switch to the third presentation then. It's Kornelius Nielsch, who is actually a professor at IFW in Dresden. and has been working in the project THERMOS recently that we met last year, more or less, right, Cornelius? We got in touch. And since then, we've been collaborating a lot. We also organized together, went together with Hao, who is working in both projects, the workshop in Copenhagen last year. And yes, I think I can leave you the stage. And yeah, please, Cornelius, you will talk about the results of your project. Thank you.
Is it me or we can't hear you?
Okay, now it's working?
Now it should work. Now it should work, yes.
Good.
The microphone was off and my computer was frozen for a second, so I had
to
get off.
Good.
Sorry.
Okay, let me start, I think, at the
Maybe.
beginning to introduce,
Yes.
I think, the THERMOS project. And we want to use atomic layer deposition as a major technique to, I think, modify thermoelectric materials and modules in two ways. So atomic layer deposition is a very controlled chemical deposition technique where you have a surface chemical limited reaction, and you can nicely code three-dimensional structure. And one way, what you can see on the left side, the idea is to modify grain boundaries and to use the modification on atomic scale of grain boundaries to improve, I think, for example, electronic properties, and on the other hand, for example, reduce thermal conductivity. The other aspect here is pointed a bit on the right side. We also encapsulate the whole module by atomic layer deposition to make it more stable so that it can operate in harsh environments. And I will show at the end of my presentation some of the very promising results using atomic layer deposition to stabilize magnesium-antimony based modules. I shortly introduce, I think, the, let's say, project team of the THERMOS project. It's significantly smaller than the START project. So we have 5 partners. So our expertise is in the terms of the magnesium-antimony materials and making modules. Then the second partner is Marto Knets from Nanogune in Spain, the Basque country. His expertise is on atomic layer deposition of powders. Then we have Filipe. He is, I think, an expert and a metallurgic chemist who is, I think, designing ALD precursors to develop very specific ALD processes. In terms of upscaling, Dr. Vicente Pacheco, here from a neighboring institute in Dresden, is involved in this institute. And then Hao Yin from TEGnology, you've heard at the beginning, is also involved here in the project in terms of applying these modules. I also want to shortly introduce our institute. So we are, I think, institute by the Leibniz Society in Germany. There are about roughly 100 institutes within the Leibniz Society. We are one of the largest institutes, which is focusing on material science and application of materials science. And we are roughly, let's say, 500 people working at the IFW in Dresden. And we have, I think, in my division, the Institute of Metallic Materials, about 5 teams, also 5 groups working on aspects of thermoelectric materials. The first team is by Dr. Nicolas Perez. He's an expert in low temperature transport. He is also operating the physical property measurement system lab, and he's characterizing thermoelectric material on a quite fundamental way. Then we have more from the engineering side, Dr. Heiko Reit. He is an expert on microstructuring technology, and he's developing microstructured thermoelectric devices, for example, for waste heat recovery, but also for small sport cooling And you can see on the images some of these devices grown by MEMS technology combined with electrodeposition techniques. The expert on thermoelectric materials, especially magnesium-antimony, is Dr. Ranhe. He also, I think, is running an ERC starting grant. And he is, I think, a great expert on developing Heusler-based materials, but also magnesium-antimony-based materials by mechanical alloying. Pinjun Jin, as she, I think, conducted, I think, most of the research I will present, I think, during my presentation. She, I think, refined and improved, I think, over a number of years now, these magnesium-antimony-based modules. And these modules are then later on coated by layer deposition to encapsulate these modules and makes them more, let's say, long-term usable in harsh environments. And then we have also the expertise of Dr. Amin Barami. He's an expert on powder ALD. This is also used here in the THERMOS project to coat thermoelectric powders. I will show a few examples at the end of the presentation. Okay, if we talk about thermoelectric, let's say, applications, this is, I think, mostly done up to now in terms of commercial application by bismuth telluride. And I would claim 95% of all these applications are done by bismuth telluride modules. And the biggest market is definitely the thermoelectric cooling. Maybe the second biggest is then, I think, hotspot cooling for the telecommunication sector. So you can also find, for example, these, I think, air-cooled, also the thermoelectric cooled seats. This is also definitely one market. And then there's, I think, the big promising market of waste heat recovery. There are a number of demonstrators, but in terms of actual market volume, I think it's still a rather small, I think, market, because the applications are also, let's say, less defined. And there are also, I think, for each individual application, you need quite different, let's say, module types and materials you use in these modules. What I think definitely counts when we talk about efficiency of thermoelectric modules is that T number, but it's not the only, let's say, important number, because other factors are definitely the, I think, energy output. And if we talk about, I think, waste heat recovery, I think in any case, up to now, we have wasted this heat. And if we just can recover a certain amount of this heat and produce it, for example, electricity, then I think the efficiency becomes maybe even secondary. It's more important what is the power output of this device at the end and what the cost of these devices. So we looked, I think, for this project, I think, especially for thermoelectric materials which can compete with bismuth telluride. And you can see here in both graphs, on the upper hand for the P-type material and the lower graph for the N-type material, there have been a lot of development in last, let's say, 10 to 20 years on high temperature materials for waste heat recovery, but there are very few competitors for bismuth telluride. And the one, I think, main competitor for the bismuth telluride material, which we have used here in the THERMOS project, is the magnesium bismuth antimonide, is the N-type material. You can see here the peak ZT values close to 2 at, for example, 400 centigrade to 700 Kelvin. And you have an average ZT, let's say, above 1, let's say, starting from room temperature to, for example, 400 centigrade. For the P-type material, the magnesium silver antimonide is very promising. This can be operated up to roughly 300 degrees. And a few slides later, I will, I think, mention why there is some limitation for this material in terms of temperature. But in principle, also you can see here very promising ZT values, average ZT above, let's say, 1 over the whole regime. And this is, I think, very promising on one hand for thermoelectric cooling, but on the other hand, also for waste heat recovery. Talking about the magnesium silver antimonide, which is a very promising P-type material, this material has, let's say, unfortunately, also a phase transition. And this phase transition occurs roughly in about 300, let's say, degrees from a, let's say, alpha phase to a beta phase. And you always try to, let's say, operate a device below these let's say, phase transition about 300 centigrade. And therefore, also there's a whole processing, for example, has to be keep into mind that you don't produce, let's say, the beta phase material, but the alpha phase material, but we can control it quite well for our applications. On the other hand, if you take into account stability, the typical bismuth telluride modules, they can operate up to 200, 250 centigrade. So if you take the magnesium, silver, antimonide, this is, I think, still can, use at slightly higher temperatures than bismuth telluride. The technique we are using is quite scalable. It's, let's say, mechanical alloying by ball milling. And we just take the element, put it here in a ball milling jar, let it run for a number of hours. And then we use, for example, spark plasma sintering to compact the material. And in order also to optimize, let's say, the context, we directly usually compact the compact material with the, let's say, main thermoelectric material. And this also, I think, makes the whole production even, I think, more efficient by using this one-step SPS process where we combine the thermoelectric material with the contact material. So in this project, we have used, let's say, one composition of the P-type material, the magnesium silver antimonide, and we have used two compositions of the N-type antimon bismuth telluride. They have, I think, for the N-type material, slightly different, let's say, the T-curves, and this somehow the whole material benefits. Take a look here on, let's say, the contact material. We can, I think, form, I think, rather well-defined interfaces. We have used the silver as a contact material for the P-type magnesium silver antimonide, and for the N-type material, the magnesium bismuth antimonide, we have used iron as a contact material. And since we do, let's say, segmented structure of the two compositions and put iron in between, you can see here where the laser pointer is a transition between these two N-type magnesium bismuth antimonide materials, and in between we have the iron. So when we look, for example, on the thermoelectric performance of these materials, they have very promising Seebeck coefficients with both, let's say, doping N-type and P-type. The conductivity is also very promising. If we combine it together, we can see here the red curve for the P-type material, the average ZT in the around, let's say, 1. And then we have a slightly better performance here for the N-type material if we segment two compositions of the magnesium bismuth antimonide. And then we have over the whole range up to about 550 Kelvin, very promising ZT performance. So what I will show, I think, in the first study is that we used, let's say, different types of compositions as a segment design to optimize these thermoelectric modules. So we have, I think, a composition of 0.5 antimon, then we have 0.7 of the antimon, and then we combine both compositions in a segmented manner to even, I think, obtain a higher efficiency. So when we were building, I think, roughly, 4 years ago, the first thermoelectric modules, you could see that if you use, let's say, here the lower composition of antimon, we had here efficiency up to about 5%. When we applied it a temperature gradient of 250 degrees, when we switched up to the N-type, let's say, higher composition antimon material, we achieved about 6%. And when we combined this segmented design, we achieved, I think, in the first one directly about 7%. And this is very competitive already with bismuth telluride. What is very important for the whole design of our modules that we, before we build any kind of modules, we do, let's say, simulations of the whole device about the efficiency, about the heat flows, and see how we can optimize the overall design. It turned out that for example, the area of the leg should be rather equal for the N and P type material. We also measured, for example, the contact resistance. This is very promising for the P-type material, where we have the contact with the silver, and we have a slightly elevated, let's say, contact resistance when we have the iron. And overall, I think it leads to a very promising, let's say, efficiency. So prediction first from the first, let's say, finite element simulations were about 9%. We achieved about 7%. And I've also shown that we were able to further optimize the performance. One of the questions, and also I think this makes a big difference, is about, okay, what is about upscaling the synthesis? So typically we fabricate our, let's say, thermoelectric material in batches of 10 grams. And then what was the goal was, let's go to, for example, to 100 grams. And for the N-type material, we can, easily, upscale it to 100 grams or even beyond. Whereas with the P-type material, it's up to now a bit more challenging, but there are also, some strategies, to upscale it in the range, let's say, of 100 grams, 1 kilogram, for example. We looked, then later on a bit more in terms of the simulation and also what we obtained by a simulation on what are the losses up to now and how we can further improve it. It turned out, okay, there can be something done with, improving the contact, but in general, the results are already rather promising, let's say, in terms of the overall the device. So we did, some other strategy and optimized more the geometry of our, let's say, overall device to obtain higher efficiencies and also higher power densities. So the first design that had just, a filling fraction of 16%. So 16% of the area of the device was just covered in principle when we looked on top, let's say, by the thermoelectric material. And so we worked on, different modules with different, with enhanced, filling fraction, starting here from 16% going to 49%, and then the densest, device was about 64%. And by this strategy, we could, further improve the overall, the device performance by using this higher density. And you can see it, in this right plot. So we obtained nearly, 9% efficiency by using, for example, the densest device with a 64% efficiency. And also the power output of the whole device significantly improved by using this denser placed, device. So the overall performance was now the maximum performance was about here 8.5%. We had the temperature gradient or difference applied of 260 degrees. And if you compared, for example, the performance of our device with a number of reference data, you can see that we are very competitive with telluride modules, but also with other references of magnesium-antimony based modules. So we have a very steep increase of, let's say, just applying 250 Kelvin and having already 8%. And there's definitely, more, room for improvements going beyond 10% by using this device. So we also looked, then later on, how to further, improve this thermoelectric device, or especially the material from the material point of view. And one of the specific features or characteristics of the magnesium-antimony based materials is that you need rather large crystal size. So for bismuth telluride, you can, produce rather small crystals, and even improves the thermoelectric performance by keeping nearly the same electronic properties, but on the other hand, reducing significantly the thermal conductivity. Whereas in the magnesium-antimony based compounds, you need rather large crystal, ideally single crystal, but this is, too expensive. But nevertheless, optimize the synthesis approach and obtain large crystal, the mobility of the electrons increase. And by this, the overall electronic properties are then superior. And one of the strategies to improve, the crystalline phase was, optimizing the compactation by spark plasma sintering. You can see here a series where we applied different temperatures, starting from 973 Kelvin, going up to 1073 Kelvin. You can see the crystal sizes was significantly improving. And if you look, for example, here of the thermoelectric power factor, the Seebeck square times the electrical conductivity, you can see a significant improvement up to 46%, for example, if you see on the results at room temperature. Another strategy was also to look on, can we all use, different dopings to optimize the performance. We, in this case, used yttrium, for example, use this yttrium doping. This also improved, for example, the mobility compared to, for example, using the doping of tellurium. And this was another, let's say, small step to improve then the average to the T of the material to 1.1. So when I think bring all these improvements together, in principle, the 3 improvements, using the yttrium as a dopant, improving the compactation, I think, process, and also, I think, optimizing the geometry by having a denser thermoelectric module. We obtained in total here maximum thermoelectric efficiency of 8.5%, applying then a temperature gradient of 260 Kelvin. We also checked investigated the cooling performance, and we could directly, I think, from the beginning, I think, obtain here maximum temperature gradient when we applied here, I think, 50 Kelvin on the room temperature at the cold side. Obtain here temperature gradient of 50 Kelvin. When we applied a bit higher, I think, temperature on the cold side, we could even, I think, obtain 70 degrees. And this module is not optimized for cooling applications so far, but it already shows the potential that we can fully compete with bismuth telluride by this material system. Another, I would say, very important, let's say, improvements and also study for us was in special how reliable is this material. I mean, there are many studies on thermoelectric materials, and all these studies are also published. But if you check more here, I think in detail, how reliable are these materials, how stable are these materials, you will find out that most likely maybe 20% of these material can be actually used in thermoelectric modules. Due to the fact that they are not really, I think, thermostable, or maybe also they are not, let's say, extremely brittle and can also not be integrated. So for us, it was very important to, I think, do some thermal cycling tests on our materials. And what we do, I think, here in terms of testing our materials, is a rather harsh, let's say, process. So we take the thermoelectric module, we apply current, heat up this module on the hot side by 250 centigrade within, let's say, a few tens of seconds, and then we let it cool. We let's say, give it the time to cool it down to nearly room temperature, heat it up again, and so within 10 minutes we have one heat cycle and one cooling cycle. And this we apply several, let's say, 10,000 times to test, for example, the performance of this device. And one of the strategies to test the performance of this device is to measure the internal resistance. And you can see here, if you apply now, for example, 30,000 of these heat cycles of these devices, the internal resistance is slightly, let's say, slightly changing, but it's rather, let's say, rather stable in this device. If we compare it with a standard, let's say, bismuth telluride module, this module is not, let's say, capable to I think, survive this rather strong, let's say, thermal shock. So it will, I think, die much earlier. And this first test, they were done directly under inert atmosphere in a glove box system. So then the goal was also, I think, to look how it's behaving outside, let's say, in real environment, like, for example, air. Before I come, I think, to the cycling test in air, I also want to shortly show here some results where we have also, I think, investigated, I think, the interfaces between the contact material and the thermoelectric material before and after this testing. And you can see some degradation of the device, but overall it keeps, I think, rather stable, I think, properties. The weakest part of the whole device is up to now the soldering material. So then the next test, we directly applied the atomic layer deposition, which has a very, I think, nice feature that we can code any kind of three-dimensional structure. So we take these modules, the fully assembled modules, put it in an atomic layer deposition reactor. And also you can easily also upscale this processes code, for example, several tens of modules within one run, for example. And we used, I think, two different material systems to I think, test the stability of our modules. The one in the first, I think, test, we use aluminum oxide. This is, I think, a very, let's say, standard material. And there you can see that the module gets much more stable compared with the uncoated module. This survived, let's say, only, let's say, a few thousand cycles, where we could at least run 25,000 cycles with using aluminum oxide. But if we switched on to hafnium oxide, then we got a much more, let's say, much more robust, I think, material. And one of the main arguments why hafnium oxide even behaves much better is the effect that I think we don't have any solid state reaction between magnesium or magnesium oxide with the hafnium oxide. Whereas if you have aluminum oxide, there are some, let's say, exchange reactions, solid state chemical exchange reaction happen with the magnesium oxide, and this makes it overall the module, let's say, less stable. One question which also quite often arises, why taking hafnium oxide? It is the hafnium oxide is one, let's say, standard material in the ALD community, which is used, for example, especially as a high gate dielectric electrode in DRAM, the microprocessor. Therefore, we have used the hafnium oxide, but there are definitely also some cheaper alternatives like silicon oxide, for example, or zirconium oxide available for the coating of the whole module. One of the features I want to mention especially is that we could also, I think, do some robust test of, let's say, several thousand cycles in air, also with the hafnium oxide coating. And if we do, for example, after this long-term test, in principle, remove the soldering and resoldered the whole module, we can see that we came nearly back to the initial, let's say, behavior of the whole module. So we can see that in principle, there's no degradation of the thermoelectric material if we pack it in hafnium oxide. There's some slight degradation if we pack it with aluminum oxide, but the weakest point in the whole device is up to now the soldering, but it's still already rather good for application. But we can, I think, go to more robust solders in the future to make it also more durable, the module, for really long-term, I think, applications. At the end, before I come to the end, I also want to briefly mention the application of, let's say, powder-based, let's say, ALD. Here we have used just a model system like copper nickel, which we coat by different oxides, for example. Here we have used, for example, zinc oxide, aluminum oxide, and we can conformally coat this loose powder before we compact the whole thermoelectric material. And if we, for example, apply it here on this model system, this, I think, coating, this powder coating, we can see that here the thermoelectric performance has been, let's say, significantly improved. Also, the overall performance is rather low, but you can see that from the principle, it works nicely that we can modify the grain boundaries on an atomic scale by using this technique. And within the THERMOS project is currently also used, for example, to use magnesium-antimonide, magnesium-silver antimonide powders, for example, and these are coated, for example, with, for example, copper at the moment. Okay, let me come to conclusion of my presentation. So I've shown that we can, I think, we have developed, I think, very high-performing tellurium-free thermoelectric materials by a quasi-fast and, I think, very scalable technique by mechanical alloying. We obtained, in terms of the thermoelectric generator, efficiency of 8.5%. Maximum cooling temperature was 72 Kelvin. The stability is rather, I think, extremely promising when we do the encapsulation by hafnium oxide in our modules. And I think we are currently working further in this interface modification of our modules. And to the right side, you can see, I think, one of the most recent, let's say, images of our modules. This is a module with a size of 25 times 25 millimeters. This has 65 legs, and we are producing these modules in, let's say, relatively small, let's say, series within the THERMOS project, and these are then integrated in a number of, let's say, different applications. And at the end, I want to especially thank, I think, the MR network for this general funding, also a number of other funding agencies like the German Science Foundation, the ERC, let's say, the European Research Council, a number of collaborators, I think, for example, the Max Planck Institute for formerly iron research, now I think called, I think, for sustainable material, and also I think a number of other groups like the group of Vicente Pacheco or also Professor Zifeng Ren at Houston University. And many thanks to the different, let's say, thermoelectric teams and also the ALD teams for the contribution to this work. Thank you for your attention.
So, thank you, Cornelius. I have some technical issues at the moment with my computer, but I hope you can hear me.
Yes, sure.
Yes. So I'd like to open the discussion. Congratulations for all the data that you showed. I think it was really impressive. And I hope there are questions now. Yes, you can stay. You can stay.
Yeah, sometimes my camera is shutting up. So.
Yeah, I see a question from Ria Thomas. How reproducible are the magnesium-antimony-based materials being synthesized for thermoelectric generators, and what steps are being taken to ensure consistency in their performance? This is the first question. There's another one.
So we are, I think, working already about 5 years with the material system, and I would say it's very reproducible. I mean, there are still some small rooms to improve this material. So, for example, for the magnesium-silver antimony, there are still some small traces of impurity phases in the material.
Yeah, it's fine.
We try to, let's say, minimize as small as possible, and there can be still some optimization done, but it's very reproducible in the whole synthesis process.
Okay, and the second question is, what strategies are being used to minimize or eliminate the negative effects of secondary phases in these materials?
Also one of the strategies we have done, we have used it. We have tried to get very pure, let's say, source material. This is also part of the THERMOS project, especially the magnesium one. This can contain, if you buy it from a number of suppliers, contain rather high, let's say, amounts of oxygen. And by reducing the oxygen amount, this is usually not mentioned. So if you buy, for example, a 5,9 pure material, very often it still contains very high percentages, I think, of oxygen. This is not covered in this purity. But if you refine it and work with rather pure, for example, magnesium, this helps strongly, I think, to improve the overall quality.
Right. Another question from Radion. Did you optimize the carrier concentration of the materials for the segment thermo element?
We have, I mean, in principle, the carrier concentration was somehow modified by using this different composition. So by changing the ratio between the bismuth and antimony, this is one option to modify it. And the other option, and what we also do, is in principle, you can use, for example, the dopant, like yttrium, for example. You can, I think, also change here the composition of the yttrium, and by this adjust the composition, the carrier concentration. But for us, it's quite important to see where's, for example, the peak ZT can be, for example, getting a higher ZT at room temperature. These are strategies where we're looking to improve the overall, let's say, the material and the device.
Any more questions? I don't see. You can also switch on your camera and microphone if you want. If you don't want to type all the time, it should be possible. Another question. How close are magnesium-antimony-based thermoelectric generators to commercial viability, and what are the key challenges still being addressed?
Okay, so there are, let's say, still some challenges, I think, and also some of the challenges we have, I think, I would say, observed, I think, doing our THERMOS project. So one of the strategies is upscaling the P-type material. This is, I think, there are ways, but we have to invest, I think, further time to improve it. Then also the mechanical properties of the P-type material is, this material takes more time to, for example, to dice it. There's definitely some demand. And also, if I compared with the production of bismuth telluride, we cannot use, let's say, for the production directly, as, for example, water-based processes for dicing the material. So we have to use to switch to oils, for example. This will change somehow the production of these the modules compared to bismuth telluride. So we cannot directly come with our material in a bismuth telluride, let's say, module, or I think fabrication line, and directly put in our material. So we have to modify some of the fabrication process of the material. But I think this is all doable. This has always a lot of small steps, but can be done.
Right. Anyone else for Cornelius? If not, maybe I can call the other speakers again to the stage and maybe have some more questions there. There was one question, for instance, for Hao that was not replied before. Let's see if I can find it. It was more, I think, a career question, I think. So maybe it's for everyone. Everyone might have an opinion there. So there's a PhD in physics currently with a postdoc in thermoelectrics and trying to understand the transition from academia to industry. If there are any suggestions for initial steps or directions to explore. It's not a technical question, really. Who wants to say something?
I can start.
Yeah.
I think it took me scaringly 10 years to do this transition, but I don't think it would take that long again, because lessons have been learned, and one thing I want to bring on the table you can consider is that now all this renewable energy, that's the hottest topic, right, in the society. But that also means that within this renewable energy, for example, windmills and solar panels and biomass, all that, the competition has become more and more severe for the existing manufacturers. So that's actually, on one hand, it's more difficult for Thermoelectric to compete with this specific technology, but it's also easier to fit TEG into the existing solutions. So think that way, we don't compete with the existing technology, but supplement and make the solutions more efficient. And with that, I think it's sort of a shortcut to the industry in terms of thermoelectrics.
Yeah, in fact, you were thinking of using the solar panels as Trojan horse to bring thermoelectrics, right? So that's an idea.
But we would, I think, most likely need a different matrix. I mean, so far we are more, I think, if we look for modules, they're more on the square centimeter scale. And so for, I think, solar panels, we really have to think about square meters.
In a way, this brings also to the fact that we are trying to organize a workshop on this, more or less this topic. So bringing the academic experience into actual production. This is something that we would like to organize for the next European conference on thermoelectrics, for instance. So please stay tuned. Okay, any more questions for our speakers, for any of them? I don't know, any or do you want to ask yourself something among you?
Yeah. Now it's good to see that we are kind of converging on the kinds of materials to use in these TEG modules. So it's the overlap between THERMOS and START. You can see that these materials are clearly some of the chosen ones, which is something that we have faced in the past, that, okay, if you explore 10s and 15 types of materials, you don't really know which are the stable ones. And if you have to make them stable, we should focus on one class. And I think that's important.
Getting closer to the, let's say, photovoltaics, let's say, research activities. They're much, since I think the last 10, 15 years, much more focused on very few material systems, I would say.
Yeah, indeed.
I mean, in the thermoelectrics community, I would say this also, bismuth telluride is still a very dominating material. This has not changed. I mean, if I look at the number of papers on P-type bismuth, let's say, antimony telluride, there's still a huge amount of papers. But I think it's now converging more towards, let's say, less materials, I would say, for specific, more specific applications.
Mm-hmm. Yeah, and I also think the cost effectiveness is the key more than the performance itself, or the cost. It's really the ratio between the performance and the cost.
Right.
And this is also to go more into our research. I mean, we have to think about each principle. I think when we further develop, I think our devices to higher TL levels, what specific costs are created by which, let's say, processing steps, I would say. When we have to make our material, definitely. But how do we assemble, for example, our module? There's probably a lot of ways to optimize the costs, I would say.
Yes.
True. And also some materials, for example, lead telluride, right? It's to many extent, it's a good material, but it's just not practical, right? It's impossible, nearly impossible to produce this in Europe. So
because of regulations, I mean, or?
Because of lead, and
okay.
At least technology, I cannot imagine how we start producing lead telluride. How can we get access to lead? Then we will probably be kicked out immediately to the science park we're staying here. It's just a thing, right? The material itself, when you have the compound, is pretty stable, it's non-toxic.
But the
from raw material to the final product, there's no magic. Someone has to get access to lead.
Right.
It's not going to happen.
I don't see more questions from the audience. Is the shyness increasing with time? People getting tired, maybe? Right. No, I don't see any more.
But I think they know where to find START.
Yeah, okay. For the project, for sure, and they have I think they know because they have been registering on the website, so they should be aware of where to find us. We will publish in the future the results, and we will have more webinars to explain them. For Thermos, I think you are finishing in the summer, right? Probably
summer or fall. It's still, we are, let's say, discussing in extension by a few months, but in principle, a lot of activity will continue. So there are also a number of follow-up, I think, projects. I think we have the Inferno project, which goes more towards waste heat recovery. There's also, I think, now a so-called STAR project here locally with Vicenzi, where we also develop a number of high temperature modules. So this will go on.
Right. Okay. So then I thank you again, as I don't see any more questions. Thank you for your time, for explaining everything to the and raising some debate, let's say, on the possible future of thermoelectrics. As a project start, we'll continue pushing for that. And please keep in touch. Thanks to all participants. We were more than 40 today. And yeah, see you again. Follow us on the social media, and get in touch if you want to have more information. Thanks again.
Thank you, Bruno. Goodbye,
have
everyone.
a nice day, everyone.
Bye.
Bye-bye.
Thank you.